No coffee. Hello and welcome back to Calculus 1. Limits at infinity to oppose the infinite limits from the first one. So, what's the form? Form is limit x goes to positive negative infinity of f of x is going to be, let's say, some L. Contrast 2.4, limit x goes to a of f of x to give me positive and negative infinity. So, the previous lecture, the answer was infinity. This lecture, the input is infinity. Now, you might be saying, well, wait, hold on, what does that mean? Well, that means that, in certain cases, for certain functions, if your x is allowed to grow, to go to infinity, the y value might settle to a number. And we'll see many examples and applications later. But let's start first with y equals 1 over x. So, when you draw that function, I am observing this side of a graph, let's say, and what I see is that as the x goes to positive infinity of 1 over x, the answer is 0. Do we all see that the y value goes to 0? In the orange circle, you need to be able to pick that up extremely quickly. A glance, and you immediately know. So limits are providing y value answers. What is happening with the black line approaching the x-axis? What is happening with the y value of the black line approaching the x-axis? The y value of the black line in the orange circle there is going to 0. On the other side, the blue side, we have a limit x approaches negative infinity of 1 over x, and it's also going to 0. On the blue side, it's climbing up to 0, so the y values are climbing up from negative whatever they were to 0, and on the orange side, they are falling into 0 from higher y values. And that's it. That's the lecture, right, on limits at infinity. So the limit at infinity could be settling down to a value, and in this case we see that value is 0. So now that gives rise to what we call horizontal asymptote. So horizontal asymptote, AJ. So horizontal asymptote is a horizontal line where limit x goes to positive or negative infinity of f of x is equal to L. Horizontal asymptote is at y equals L. Now, some specs for horizontal asymptote. Number one, horizontal asymptote can be crossed locally. This is very important to understand because horizontal asymptotes have to be obeyed at infinities. So you are going to run eventually in a problem. Let's say will look something like this. And then you will have a piece that pierces through the asymptote inside. So they have to be obeyed at ends, but they don't have to be obeyed here. So yes, yes, and they don't have to be obeyed there. So function can cut through horizontal asymptote. Keep that in mind for chapter 4. Number 2, slant asymptote. Slant asymptote is the offshoot of the horizontal asymptote. You can't have both at the same time, so it's one or the other, or neither. Slant asymptote only happens in rational functions. Where you have x to the p divided by x to the q when p is equal to q plus 1. So if the degree on top is by 1 bigger than the degree on the bottom, we do use long division of polynomials. To get y equal mx plus b, which is the slant asymptote, SA. So slant asymptote, let me just add SA. And again, we are going to use this a lot. So let's see some of the examples of the horizontal asymptote. Y equals e to the x. If you look at the e to the x graph, it is clear that it has limit x goes to negative infinity of e to the x is equal to 0. So we do have an asymptote, and the asymptote is going to be the value L, right, which is 0. So horizontal asymptote at y equals 0. That's an example. Another example that you will see in your future math courses is y equals inverse tangent of x. This is an amazing function because it gives you two horizontal asymptotes. So there is going to be a horizontal asymptote at negative and positive pi over 2 on y-axis. And the graph is going to snake through like this. And we see our, over here, limit x approaches positive infinity of tangent inverse. X is going to be pi over 2. That's the upper one. And on this side, limit x approaches negative infinity of inverse tangent of x, which is giving us negative pi over 2. To give you another example, go with the applied example here. If you studied population, so let's talk about biology. So you studied population, you might know that exponential models are used to show population, but the exponential models are not too good, basic ones, because they have this issue of shooting to infinity. Right, so if you are looking at the population, being that this is your initial population and you have your time, and the y-axis is the population, you see that exponential model is bad. Because you're starting with initial population at time equal t0, right? Equals 0. You started with p0 and it just shoots to infinity. You can't have population shoot to infinity of anything, because everything is finite size. On this planet, there are different school of thoughts, but on this planet, scientists are arguing that the planet is able to comfortably support between 10 to 15.2, I believe, is the highest carrying capacity. Meaning that when population reaches or exceeds that number, it's not going to be pretty to live on this planet anymore, because of resources, right? The land on which you are going to build is finite. However, the oceans are rising and swallowing the land, and deserts are always expanding. The wind is blowing the sand out. So, expanding deserts and rising seas. We are not really people that live in those conditions very well, right? So, as we have less and less land on which we can live on, right? More people means more food, more resources, more everything. So there's the cap on that one as well, right? So when you take a look at the situation, right? Some scientists would say, okay, you can, I don't know, 10.5 billion and then we're doomed, or 15 billion and then we're doomed. Well, we are at 7.5 billion now, so we're doomed either way. It's 5 minutes to 12 in that respect anyway. But this would be a bad model, right? It's bad model because we are not expecting infinite rise in population. There is another one, logistic model, which is much better to describe situation with the population. It also starts with the initial P0 population. It rises exponentially and then it levels off. Now that's the one that has this K value, and this K value would be that carrying capacity of the planet. Now it doesn't have to be just population like this. You can think of other situations when you can use this, but now I'm going to say that the limit as time goes to infinity of the population is going to be equal to K in this one. So it's a horizontal asymptote, right? It's the maximum value that can be reached. When you go up, that's the maximum value you can reach. And when you look at that graph, you can think of other instances where you can use this. And I'll tell you which ones. For instance, one of these would be battery charging. So storage of energy on this one. So you charge over time, and the battery approaches the 100% mark. Your battery is never 100% full, even though the screen shows 100% full. No. You always have some chemical that is not converted to the other that stores electricity. And then when you go and, so that's one, battery charging, population, then what else can we do? I have like 15 examples in my head like this, ready and now, like, what am I thinking? Don't see this. What else? No, but let's talk about, because that one is, you know, capped at 30. Oh, you mean the carrying capacity because the number of chairs? All right, sounds good. The number of people that can get sick with a particular strain of disease, we're still here as a species. There were plagues in good old times when people didn't know they're supposed to wash their hands. So plagues were going around. At one point, actually, plague wiped out 2/3 of the population of Earth, of people. 2/3 of everyone. So that means 2/3 of every country that came in contact with that was wiped off. Now, some people have natural immunity to diseases. You know that there are people with AIDS walking around, they are carriers, they will never get sick, they will never die from it, right? They can get others infected and someone else can get infected and die instantly, right? So that's possible. Everyone's body is different with different antibodies and structured differently, you know, all unique snowflakes. But in a situation where you have a population that gets infected, there is the carrying capacity. These are all of the people that could possibly get infected, animals or whatever, and then there will be a portion of population that will not, even if they get infected, nothing would happen. And that goes for everything out there, which is why we are still around. If we were all susceptible to all diseases equally, which is, again, I told you, we are not born equal, we would be wiped out as a species a long time ago. The first plague that came around would just wipe everyone out, and that will be it. So we have to be careful. Computer viruses, the same idea, right? They work on the same principle. And then cleanup and all of that stuff. So these are all examples for horizontal asymptotes where you get to take the limit and look at infinity to decide. So you see that over here, x goes to positive infinity. So I drew orange circle above and said as x is going to the right forever, you see that the y value of the function is getting capped at pi over 2. So this is what they taught, right? This is what they said, speed limit. Limit doesn't mean maximum, right? It means speed limit. So your suggested speed limit is 65, right? And that's it. Now, we all know, right, that the horizontal asymptote, which is 65 miles, can be pierced, right? Because do we have anyone driving at 65? Obviously, everyone drives 65 on 55. Bad people, and I associate myself with you. Anyway, next concept, and this is something that you did not have with the vertical asymptotes and previous lecture, and this is the end behavior, another concept from pre-calc. Right on time, end behavior. So we have end behavior, and that is a way to express what is happening on the end sides of your function. You see, if you draw x squared, you have these two going off up, but they're also at the same time going to the left or right. So if I color code these, let's go with the orange over here, you see that this x is going to negative infinity because it's going to the left forever, right? Do we all see that? And you're getting positive infinity on top, and this one is limit x goes to positive infinity x squared. You're also getting positive infinity. This is known as end behavior of the function. You studied this in pre-calc, and in pre-calc they gave you a chart of possibilities, which are only 4, obviously. And we get to recycle that chart now, except we get to put our fancy limits. The only 4 situations that you can have, other than obviously horizontal and vertical line, is your function going that way, your function going that way, your function going this way, and function going that way, right? There are no other possibilities. Because if you say, oh, but what about this? It's the same thing. It's going to the right and up. I don't care which way you draw. Like this. So, goes up this way, goes up that way, goes up, doesn't matter. All 3 of these are going up plus right. All 3 of these arrows. So we just draw one of them. We don't need all of them. So, to represent this 4 possibilities for end behavior of any function you can possibly draw, you would say limit x goes to positive infinity of f of x is positive infinity. For this one, you have right and you have your up. So this is a mathematical way to write right and up. So bring this up next time when someone says, what do you know? You know this. Now you have this one. It's going to the right and down, negative infinity on the y. So this one going to negative infinity on x, negative infinity on y, and finally this one. So these are your 4 end behavior that your function can show. So now, if you observe going back to e to the x example, actually we can do the decay. Let's do decay. Decay model. So this is our graph. It goes through 1, and we have these 2 ends. So now let's say orange end over here would be end behavior. We have the limit x goes to negative infinity of e to the negative x equals to positive infinity. So that will be end behavior. And the other side here is the one that tells us there is an asymptote, because limit x goes to positive infinity of e to the negative x is equal to 0. So when your input over here, when your input is infinity, which matches our form, input is infinity. So when your input is infinity, you have two possibilities for the answers in this lesson. One is infinities, in which case you are getting end behavior. The other one is solid L, as a definition set up there for horizontal asymptote. So what is the typical question on the exam? 1. Typical question is prove that function blah 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 has the vertical asymptote at x equals 2. Are there any horizontal or slant asymptotes? Right. So to find that, all you need to do is to take the limit to infinity. So let's see. Are there any horizontal asymptotes in y equal x squared plus 3? Are there any horizontal asymptotes in x squared plus 3? You immediately take the limit. You know, because you learned the red definition up here. It says, whenever the function is given to you, take the limit as x goes to infinity. Perfect. Let's do that. Limit x goes to infinity of x squared plus 3 is equal to, well, it's equal to infinity, because infinity squared plus 3 is still infinity. So no horizontal asymptotes, because this did not turn out to be a finite value. It has to be a finite value, just like here. Because when the finite value is, let's say, 0, then your asymptote is at y equals 0. Well, we got infinity. So y equal infinity, that can be an asymptote. So no asymptotes there. And let's take a look at some spicier functions, like something rational. How about f of x is equal to x squared plus 3x minus 6 divided by 4x squared plus 1. Do we have any horizontal asymptotes here? Now, if you remember, you remember those 3 rules from pre-calc for horizontal asymptotes? Something with exponents and...
Oh yeah, you divide with, let's say, x squared over 4 squared, you divide 1 over 4. So that would be the asymptote, yeah?
When they have the same powers, right?
Yes.
What happens when the powers are different?
It would be none. It would be either none or it would be undefined. Or 0.
Yeah, okay. Hard to remember, right? How about the rest of the class? What are the exact rules? Now, I'm not going to get upset at all that you don't remember it, because we're just going to learn a much better tool, right? Those rules that you are remembering, those rules work only when these are polynomials. Now, I changed this over here with e to the x, and those rules don't apply anymore. So now we need to understand that if you want to find horizontal asymptote, you now learn the definition which says find the limit. So we go and we say, okay, limit x goes to infinity of x squared plus x squared plus 3x minus 6 divided by 4x squared plus 1. And we need to solve this limit. If we get finite value on the other end, then that's the horizontal asymptote. If we get infinity, then that means no horizontal asymptotes. So the way to do this, and you should write this down because this is the way to do the problems, you divide by the highest exponent. So now this becomes limit x goes to infinity 1 plus 3 over x minus 6 over x squared divided by 4 plus 1 over x squared. Now, what limit laws do from last class, limit laws take the limit and assign limit to each one of these individually. So now you have limit of 1 plus limit of 3 over x minus limit of 6 over x squared divided by limit of 4 plus limit of 1 over x squared. So these are obvious, right? 1 and 4 are obvious. Now the rest, what's the limit of 3 over x? As x goes to infinity. All of these limits are x goes to infinity, everywhere. Zero, 1. Yes. Good. How about we do the experiment for now? Behold 1. Right? We already, this is 1. 1 paper. Right? I could have done this by asking for volunteer, but this is a less gory example. Let's make, let's divide this by 2. See, this will be the messy part if I ask for volunteer. Like right here. Right now. I wore the color so it doesn't show, but then carpet, the first row over here is messy. So what do we have? We have 1. And when I say divide by 2, that's the answer. Now, look at the answer. The answer is smaller than what it used to be, right? Now, if I decide to divide by 4, which is making denominator bigger, so it used to be a half, and now it's this much. It used to be 1, now it's this much. If I divide by 8, that means we get that. Here's your 1 divided by 16, 1 divided by 32. There are 32 of these in the full paper. So do you see what's happening with the y value as you keep increasing the amount of cuts? Remember, your amount of cuts is going from 2 to 4 to 8 to 16. Now it's at 32. So denominator is at 32. I'm only at 32. Look at the size of where 1 was and how much I'm getting now. This still has to go to infinity. I'm at 32. So 64, and then 128, and since I'm there, 256, and here is the 512. Yes. So this is 1 divided by 5, 12. That's nowhere near infinity. So what happens with this y value that I'm holding as the x on the bottom is going to infinity, which is the amount of cuts that I'm making? What's going to happen with this? This is at 5, 12 now. What's going to happen with this? It started on this size, and now it's this big. As I keep cutting, what's going to happen to it? And eventually, be nothing. How do we write nothing in mathematics? Anyone? Yeah. 0, thank you. So that's why each one of these that has x in denominator is going to shoot to a 0, and we're getting 1/4. So now,
you said divide by the highest asymptote, when you divide everything by x squared?
Highest exponent. Yes. So, limit of 1 over x to the n as x goes to positive, negative, infinity is equal to 0. This is a formula for you. The 2 over the top. Good. It's visible. Now, this n can be any exponent bigger than 1. Good. Yay. So, to recap real quick, limits at infinity. We are looking for input to be infinity, which is contrasting the previous lecture where the answer was supposed to be infinity. We learned the definition here, which says that to have horizontal asymptote, your limit when input is infinity must be a finite value. Like we got, it was a good effort, 1/4, right? And then we just did a whole bunch of examples. And then we talked about the end behavior. So what happens if you are working on a limit, you are not getting a finite number, you're getting another infinity. So infinity is the input and infinity is the output. Well, you are running into one of the 4 cases of ending the function, right? And you just make sure that your inputs are infinity on the left, inputs are positive on the right. Positive answers on top, negative answers on the bottom to go down. And that will be the end behavior of the function. And then examples on figuring out the row. I think also the growth rate of functions. I should have logged on. I think the growth rate of functions might be the part of this as well, which is cool thing to know, and you will expand on that in your calculus too. So, growth rate of functions. this is important because it speeds up your taking the limits. All right, so here we go. Chapter 2. Huh, it's not here actually. Okay. Yeah, it's not here. So we'll get to it when we get to it. Trying to remember which section it belongs here, but it could be somewhere in chapter 4. Anyway, e to the x is faster than x squared. So e to the x is faster. This is just an example of what it's going to be. So e to the x is growing faster. You can test that very easily by figuring out, or actually we can do 2 to the x. So x squared and 2 to the x. So we have x squared 1, 2, no, 4. 3 squared 9, 16, 25, 36. So these are all the square numbers. And 2 to the x is 2 to the 1. 2 squared is 4. 3, so 2 to the 3 is 8, 16, 32, 64. And you see how it just took off eventually. Right, they were neck to neck in this region here, and then it just takes off on exponential side, as you can see, because this one is still in 30s, the next is 49, this is 128, it's just gonna explode. Oh, I can make a snowman. Yay, there we go. Great. I'll see you all in the next lecture. Bye.